Your lecturer is Don Lincoln. Dr. Lincoln is a senior scientist at Fermi National Accelerator Laboratory. He is also a guest professor of high-energy physics at the University of Notre Dame. Dr. Lincoln received his PhD in experimental particle physics from Rice University. His most noteworthy scientific accomplishments include being part of the teams that discovered the top quark and confirmed the Higgs boson. The author of 4 books and many magazine articles, Dr. Lincoln has given hundreds of lectures on 4 continents and to a broad range of audiences.
Dream no small dreams, for they have no power to move the hearts of men. This quote by Johann Wolfgang von Goethe is still powerful today, 2 centuries after he first wrote it down. It doesn't matter whether you're trying to broker an international peace treaty or cure a disease or change a society. It's not the incremental improvements that stir the blood. It's the big ideas. In science, humanity has had great success over the centuries. Isaac Newton's amazing ideas about gravity were the first major scientific steps towards a theory of everything, ideas that we still use to guide our space probes to distant targets, like when the New Horizons spacecraft buzzed by Pluto. Our mastery of the atom made chemistry possible and also allowed us to build electronics and computers that can calculate faster than human imagination. Each of these achievements is big in its own way, but they aren't the biggest possible. While there's no denying that these ideas originated from a grand dream, each represents merely a single facet of human knowledge. The ultimate goal of science is much bigger. The ultimate goal of science is nothing less than an understanding of the fundamental rules of the universe itself. That's a pretty ambitious goal, and it depends crucially on the idea, which seems to be a fact, that all of the phenomena we see around us are interconnected and arise from even deeper causes. There's a class of scientists who keep asking why, with each answer resulting in yet another question. An example of this might be like asking why the sky is blue, the answer for which is the size of air molecules. Asking why air molecules are the size they are leads to the size of atoms in those molecules and the strength and the nature of the forces that hold them together. The next obvious question would be why atoms have the sizes that they do, and that's because of the laws of quantum mechanics and the properties of protons, neutrons, and electrons. We do that over and over and over again, and the hope is that one day there will be no more questions because we understand the reasons for everything. I did say that we dream big. So let's get down to business. While big ideas are where a final theory will originate, we won't know that we've succeeded until we've rigorously tested it against measurements. That's because details are important in science. Every theory and every observations need to fit together perfectly because all it takes to kill a theory is a single confirmed disagreement between measurement and prediction. To get a feel for what that means, we first must understand existing theories and the rigor with which they've been tested. Ironically, to successfully dream big, we need details. But disconnected details are meaningless unless we understand the bigger picture. Without an understanding of the bigger picture and how things fit together, details can seem like just a whirlwind of disconnected facts. So that's where we'll start, by getting an overview of current thought. Just what are our current prototype theories of everything? Over the centuries, scientists have combined their thinking and observations and distilled them into 2 distinct theories. The first is Einstein's theory of general relativity, which is our best description of how gravity works. Like Newton's earlier theory of gravity, general relativity covers everything from what you see when you drop a ball to the stately motion of a swarm of galaxies. But it also includes things like black holes, gravitational waves, and the nature of space-time. That's gravity. The second theory is called the Standard Model of Particle Physics, and it covers everything else, from atoms and chemistry to light, radiation, and far, far more. So let's talk about each of those theories in turn. Let's start with the Standard Model. The Standard Model explains everything except gravity. Why does a soda fizz? That's the Standard Model. Why does the sun burn? The Standard Model. The screech of fingernails across the chalkboard? The Standard, well, you get the idea. So, if I ask you to start explaining why things work the way they do, you might begin with the weather, the earth under you, or maybe the cycle of life, which means that perhaps you'd start with the scientific fields of meteorology, geology, or biology. But no matter your starting point, if I asked you a few pointed questions, the conversation would quickly turn to chemistry. In the example of weather, it's the evaporation, transportation, and precipitation of water that matters, along with how the gases in the atmosphere heat and cool and move. So let's talk a little bit about chemistry. When you think about it, chemistry is really pretty complicated. Liquid water, ice, and steam are all the same thing. A soda fizzes because gas is mixed with liquid under pressure. If you mix chlorine, which is a deadly and poisonous gas, and sodium, which is a metal that reacts violently when it encounters water, you get sodium chloride, which is ordinary table salt. The fact that matter could exhibit so many different kinds of behaviors was incredibly mysterious. It was made less mysterious in the 18th and early 19th centuries when a legion of early chemists discovered that there were several fundamental substances that they called elements that seemed to combine together in different configurations. Chemistry occurred when the elements combined or broke apart. Another key clue was revealed in the early 1800s when English scientist John Dalton discovered that when elements combined, they combined in fixed ratios. Essentially, what his work did was verify that atoms existed. People had talked about atoms for over 2,000 years, but it took until the first years of the 19th century that we had experimental data that verified the idea. And, with the discovery of atoms, our understanding of the behavior of matter had one of its first unification moments. All matter was made of atoms of elements. Having this new unit of measure also made it possible to begin organizing even more observations. There were highly reactive elements and ones that were less so. Some elements like to interact with other elements more than others, and some mixed in a couple of ways. For instance, carbon monoxide, which contains a carbon and an oxygen atom, and carbon dioxide, which consists of a carbon and two oxygen atoms. In 1869, many additional observations were brought together when Russian chemist Dmitry Mendeleev invented what we now call the periodic table of elements. What he did was to take the discrete pieces of knowledge developed by a century of chemists and alchemists and to organize the elements in a big grid. You can look at a modern grid here. Columns are chemically similar. For instance, in this left-hand side, the elements are highly reactive: hydrogen, lithium, sodium, and potassium, etc. In contrast, on the right-handmost column, the elements are very non-reactive: helium, neon, argon, krypton, and so on. Each column contains atoms with similar chemical properties. When you look at the periodic table, it's a pretty amazing achievement. But perhaps even more amazing is that when he started out to work out the table, he didn't know about these 100 and more elements. Mendeleev only knew about a smidge over 50, which means that he had some holes in his table. The fact that he worked out the patterns with such incomplete information was an even more impressive achievement. It's probably worth pausing for a moment to reflect on the periodic table. When Mendeleev wrote it down, he didn't know why the elements had the properties they do and why the patterns repeated. In fact, answering those questions would take another 50 years when we finally understood the nature of the atom and the laws of quantum mechanics. All he knew at the time was that some elements reacted similarly and that the mass of these similar elements were different. But those two observations led him to his key insight. I dwell a little on this periodic table because there was a point, say in 1880 or so, where the very best scientific minds in the world would look at the periodic table and wonder what those patterns were telling them. It would take the unifying ideas of nuclear and atomic physics to explain the mysteries of chemistry. In many ways, that's where we are in our modern effort to develop a theory of everything. We know of patterns, but we don't know the underlying causes. And this, more than anything, is why we have such enthusiasm for the idea of unifying theories. It's because we've seen many examples of when patterns eventually turned into understanding. All right, so let's talk about a more modern understanding of atoms. Atoms have a particular structure with a small and concentrated nucleus at the center, surrounded by a cloud of electrons. The nucleus is made of protons and neutrons, and that's all it takes. With protons, neutrons, and electrons, we can build all of the familiar kinds of matter. The situation changed a bit in 1964 and into the early 1970s when physicists found that the protons and neutrons were made of even smaller particles still, what we call quarks. So let me start by showing you this image, which is a great way to introduce the Standard Model, one of our two biggest steps towards a theory of everything. I can't say that the Standard Model itself is already a theory of everything, but it's a theory of lots of things. In fact, while nobody claims that we're done, you can regard the Standard Model as our current best guess of a grand unified theory. That's why it's so important to understand it and what it signifies. For one thing, whatever the final theory of everything looks like, the Standard Model will be part of it. Mind you, this image isn't the Standard Model itself, but it represents all of the important components. For instance, we see here in the upper left-hand corner 6 particles called quarks. As you can see, some of the quarks are found inside protons and neutrons in the center of atoms. At the bottom left, we have 6 particles called leptons. Leptons are the lightest of the subatomic particles, and the most familiar one is the electron that is found in the outskirts of every atom. Over here on the right-hand side, we see there are 4 particles that are simply called force-carrying particles, or sometimes, for technical reasons, called gauge bosons. They are responsible for transmitting 3 of the 4 known forces. And here in the center, we see the ghostly field called the Higgs field, and a particle called the Higgs boson, whose existence was confirmed only in 2012 and was the final missing piece of the Standard Model. In the next several lectures, we're going to talk in detail about each piece of this chart so you can understand what you're seeing. The overview will help you understand how the things fit together. So let's start by talking about the known forces. We know of 5, or maybe it's 4, or maybe it's 3. The complication arises from the fact that we're living through a period of unification. Over the last few decades, we've unified forces that historically have seemed distinct. That's incredibly exciting, but it also leads to a bit of confusion. So let me clear that up a bit. I'll start by talking about the 5 forces and show how they can be thought of as 4, and maybe even 3. The 5 known forces are gravity, which keeps us firmly planted on the ground and guides the planets through the heavens; electromagnetism, which covers both electricity and magnetism, of course, but also light and chemistry; the strong nuclear force, which binds protons and neutrons together in the nucleus of atoms; the weak force, which is responsible for some forms of radioactivity; and finally, the Higgs field, which gives mass to subatomic particles. Those are the 5: gravity, electromagnetism, the strong force, the weak force, and the Higgs field. So how do we get down to 4, or maybe even 3 forces? Well, in the late 1960s, physicists showed that the weak force and electromagnetism were really 2 facets of a single thing, much in the same way that electricity and magnetism turned out to be 2 facets of something that we now call electromagnetism. Men and women are 2 facets of a single thing we call human. You get the idea. Therefore, scientists often talk about an electroweak theory. So we might say that the forces are gravity, the electroweak force, the strong force, and the Higgs field. On the other hand, the Higgs field is inextricably tied with the electroweak force, so maybe it can get tucked under the electroweak umbrella. Under that way of thinking, we have but 3: gravity, the strong force, and the electroweak complex. Let's talk a bit about the forces. We should be careful, since the word force has a familiar meaning. It could mean something like pushing a car out of a ditch, or even, these aren't the droids you're looking for. The better word is interaction, because the word interaction means that some change is caused, like changing a particle's identity without actually moving it. However, the word force is ingrained in the literature, so we'll stick with that word most of the time. The strong force is the strongest of the known forces. For example, it's the force that explains why the sun burns so very hot. So the name is apt, it really is strong. But it also has a weird behavior. It's incredibly strong over very short ranges, say the size of a proton. Once 2 particles are separated by a distance much larger than that, the strong force goes to 0. It's a little like Velcro. If 2 pieces of Velcro are touching, they're strongly bound together. but once they're separated, they feel no attractive force at all. That particular facet plays a big role in understanding the large range observed in the mass of atoms. That's the strong force. The next strongest force is electromagnetism, which unifies electricity and magnetism into a single force. It's much weaker than the strong force, but it has a different behavior as far as distance is concerned. Two particles experiencing the electromagnetic force will, in principle, feel a force between one another if they are located on the opposite sides of the universe. Granted, that force will be very small, but it won't be mathematically zero because electromagnetism has an infinite range. Because of the difference in how the two forces change with distance, you have to be very careful to specify distances when you compare electromagnetism to the strong force. So we traditionally pick a separation distance of about the size of a proton, which is a femtometer or 10 to the minus 15th meters. At that separation distance, the strong force is about 100 times stronger than electromagnetism. Of course, given the short range of the strong force and the infinite range of electromagnetism, if two particles are separated by just a meter or even a millimeter, electromagnetism is actually much stronger. The next weakest force is the weak force. The natural range of the weak force is about 1/1000th the size of a proton. However, if we ask how strong it is at the separation of a femtometer, it's about 100,000 times weaker than the strong force. When we look at the weak force at its natural scale, we see that it's actually similar to electromagnetism, and that was the beautiful insight that allowed for electroweak unification. We'll talk a great deal about this in Lecture 8, but for most practical purposes, the weak force acts extremely weakly. Then there's gravity. It has an infinite range like electromagnetism, but at the femtometer distance scale, gravity is something like 10 to the 40 times weaker than the strong force. That's a 1 over a 1 followed by 40 zeros. I say something like because you get a different answer if you're talking about the gravitational force between two protons, two electrons, or a proton and electron, but the 10 to the 40 number gives you the right message. Gravity is crazy weak, and indeed, gravity is so weak that we've never figured out a way to study it on these super small scales. If we tried to study it down there, the measurements would just get swamped by the effects of the other forces. So gravity is not covered by the Standard Model. The Higgs field is a bit different because what it does is give mass to particles. So it's not a force in the way that the others are, and you can't talk about it in quite the same way. So I can't tell you how its strength compares to the others. This is one of the times where the word interaction is more apt. The change that the Higgs field causes is to turn massless particles into massive ones. With the introduction of the forces, we're now ready to begin to get a handle on the pieces of the Standard Model. Let's start with the quarks. There are 6 different types of quarks. Physicists say flavors of quarks because, well, we particle physicists do like cutesy terminology. The quarks have kind of silly names, which are up and down, charm and strange, and top and bottom. The up, charm, and top quarks have an electric charge of 2/3 that of a proton. The down, strange, and bottom quarks have electric charge of -1/3 that of a proton. The up and down quarks are found inside protons and neutrons. A proton contains 2 up quarks and a down quark, while a neutron contains 2 down quarks and an up quark. You can check that the electric charges make sense. The up quark has a charge of +2/3 and the down quark has a charge of -1/3. So thinking in the context of charge, the proton's up, and down is 2/3 plus 2/3 minus 1/3 equals 1, which is the charge of a proton. For the neutron's quark content of up, down, and down, we see 2/3 minus 1/3 minus 1/3, which is 0, and that works out great. All of the quarks experience the electromagnetic force, but they also experience the strong force and the weak force as well. While the up and down quarks are found in stable atoms, the other 4 quarks are unstable and disappear in the blink of an eye, far shorter than a second. In fact, the longest lived one disappears in about 100 millionth of a second, and the one with the shortest lifespan exists only a half of a trillionth of a second. So the only way to study them is to create them in particle accelerators, which is what we do. All 6 types of quarks have been discovered. The quarks have very different masses. The up and down quarks have very small masses, less than 1/100th that of a proton. The strange quark's mass is higher than the stable two, maybe 20 or 40 times higher. The other quarks are porkers by comparison. The charm quark is about 30% heavier than the proton, and the bottom quark is more than 4 times heavier than the proton. But the king of the quarks is the top quark, weighing in about 185 times heavier than a proton, or about as much as an entire atom of tungsten. The top quark was discovered in 1995 by, well, me. Okay, of course it was me and 800 of my closest personal friends, and they all had something to do with it. But, don't tell my mom. Somehow she got the idea in her head that I did it myself, and, well, I'm sure you understand. So the quarks are the heaviest particles, most commonly found in the nucleus of atoms. The leptons are different. For one thing, they're generally lighter than the quarks. Leptons don't feel the strong nuclear force, but they feel the weak force, and their interaction with electromagnetic force is mixed. There are 2 classes of leptons. The first row includes the electron, the muon, and the tau lepton. They all carry electric charge, and so we'll call them the charged leptons. It's simplest to think of the muon and tau lepton as just heavier cousins of the electron. The electron weighs about 0.05% that of a proton, while the muon is a smidge heavier than 10% of a proton. And the tau lepton is just shy of being double the mass of a proton. Like the quarks, the heavier charged leptons decay very quickly, with the longest lived one existing only a millionth of a second or so. So, if you want to study them, you need a particle accelerator. The second row of leptons are called neutrinos. They don't have electric charge, so they only experience the weak force. Because the weak force is, well, weak, it means that neutrinos can pass through matter without interacting. Neutrinos are produced in nuclear reactors, and the biggest nuclear reactor around is the sun. So if you wanted to shield yourself from those solar neutrinos, you'd first have to move to the closest star, which is Proxima Centauri, located about 4 light years away. And then you'd have to fill up the entire distance with solid lead. Neutrinos really don't interact very much. And as it happens, about a quadrillion neutrinos pass through you every second of every day of your life without doing anything. The mass of neutrinos is very low. The Standard Model treats them as having 0 mass. In fact, we've discovered that the neutrino masses are actually just super small, not 0. So this fact shows a crack in the Standard Model and maybe points toward a way forward. We'll talk about the consequences of a non-zero neutrino mass in Lecture 11. So the quarks and leptons are the matter particles. You can think of quarks as being sort of nuclearish particles, the charged leptons as sort of electronish, and the neutrinos as having no analog in our familiar world. They interact so little that you might think of them as being ghost-like. So what about these guys over here on the right-hand side of this picture? These are the force-carrying particles. We talked about the forces, but not how they actually work. In the quantum world, these forces are caused by the exchange of particles. For instance, the particle of electromagnetism is the photon. If 2 electrons bounce off one another, the way that happens is that one electron shoots a photon at the other. The shooting electron recoils, as does the receiving electron. It's kind of like 2 people standing in boats located near one another. If one person throws a heavy sack from one boat to the other, both boats will move away from one another. Another force particle is called the gluon, which is the particle that mediates the strong force. The photon, which mediates electromagnetism, and the W and Z bosons, which are responsible for the weak force. Both the photon and the gluon are massless, while the W and Z bosons are very heavy, nearly 100 times heavier than the protons. It's the mass of the W and Z bosons that make the weak force look so weak. There's a hypothetical particle called the graviton that would be responsible for gravity, but it hasn't been discovered yet, and we really don't understand gravity in the quantum world. So, in our introduction to the Standard Model, this leaves the Higgs field and the Higgs boson. These were proposed in the late 1960s and were only discovered in 2012 by, again, well, me. Well, and this time it was with 6,000 of my closest personal friends, but again, don't tell Mom. The Higgs field gives mass to the quarks and the leptons and the 2 heavy force-carrying particles, and even the Higgs boson itself. We'll talk a great deal more about this phenomena in subsequent lectures. The Standard Model is pretty amazing. With it, we can explain basically everything we see, from why bread bakes, to how stars burn, and we hope one day to unify the electroweak and strong forces into a single force called a grand unified theory. However, the Standard Model is completely silent on the force due to gravity. For that, we need another theory. In 1915, Albert Einstein revolutionized our vision of the universe. Before his crucial insight, we had to make do with Newton's theory of gravity. Now, don't get me wrong, Newton's ideas were amazing. He unified the gravity of falling objects on the Earth with the gravity of the stars and the planets. Newton's ideas were really the first formal unification of seemingly unrelated phenomena. But there was an incorrect idea hidden at the very core of his theory. Newton's ideas had stars and planets marching in a stately way through a kind of space that was mathematically flat and unrelated to the objects moving through space. Einstein changed all that. Einstein described gravity as being caused by matter and energy actually bending space. Rather than space being like the surface of a billiard table, it was more like the surface of a trampoline, with heavy masses distorting the surface and causing the lighter objects to fall towards them. Einstein's theory made all sorts of seemingly outlandish predictions. For example, black holes, which are concentrations of matter that are so dense that not even light can escape from them. He predicted that colliding stars and black holes would literally shake the fabric of space and send gravitational waves traveling across the universe. Gravitational waves were indirectly discovered in 1974 and directly observed here on Earth in 2016. Einstein made even weirder predictions, like that clocks run more slowly in strong gravitational fields and faster in weaker ones. That really does sound crazy, but the prediction has been tested and it's correct. We now have clocks so precise that we can see that they tick differently when one of them is lifted a single foot higher than its identical twin. Relativity has been tested to incredible accuracy, but there's only one problem. The theory doesn't work when you apply it to the atomic or subatomic world. That is, when you mix the two, you get impossible predictions. Like when you add up the probabilities of all possible outcomes, you get values higher than 100%. So that's actually a super important message. The fact that general relativity explains the cosmos, but not the microworld, means that we still have a way to go in devising a theory of everything. In fact, one of the biggest goals of physics is to somehow first devise a quantum theory of gravity, then merge quantum gravity with the Standard Model. Or, even better, merge quantum gravity with a grand unified theory that unifies all of the other known forces. We really don't know how to do that, but when we achieve it, we'll have taken an enormous step towards a unified theory of everything. So let's pause and take stock. Our most comprehensive theories thus far are the general theory of relativity and the Standard Model of particle physics. We know that the general theory of relativity covers what we know of gravity, and the Standard Model does a passable job of covering everything else. The two are incompatible, and we need to somehow figure out a way to invent a theory of quantum gravity and merge it into the Standard Model. Then we'd be done, right? Well, not quite. While the unification would be a huge deal, indeed a crucial and necessary step, even that's not enough. For one thing, the Standard Model has its own holes. For instance, the Standard Model doesn't explain absolutely everything. While it integrates the quantum forces pretty well, there are 19 parameters that it can't predict and have to be put in the theory by hand, after they're measured by experiment. These parameters are mostly the masses of the particles, the strength of the charges for the strong, weak, and electromagnetic forces, and some parameters that govern how particles decay. A complete theory would predict those quantities, and the fact that the Standard Model doesn't means that we have some work to do. In addition, neither theory explains two substances called dark matter and dark energy, which are needed to describe the evolution of the universe. Indeed, our best guess says that these two dark substances make up 95% of the mass and energy in the cosmos. 95%. That means all of our successes cover a mere 5% of what there is to know. That's both humbling and invigorating, as it guarantees that there are big discoveries ahead of us. So there's still a lot to learn, and in this course, we'll learn about all of it, what we know and what we don't, and the directions we're thinking to try and make progress. Before we dig more deeply into the subject matter, I'd like to share a quote from Einstein that really exemplifies what we're trying to do. He said, "I want to know how God created this world. I'm not interested in this or that phenomena in the spectrum of this or that element. I want to know his thoughts. The rest are details." Now, no matter your position on religion, whether you're highly religious or a staunch atheist, you can understand Einstein's meaning and appreciate the poetry of his words. This course is about just that, knowing God's thoughts. We want to know the ultimate and underlying principles from which all other principles derive. Like I said at the beginning, we dream very, very big. But I also need to add a note of caution. Our goal is science and not philosophy. Details are important, and they are important because science only works if it all hangs together. A single, reproducible disagreement between measurement and prediction can kill a theory. As Thomas Huxley said, science is organized common sense, where many a beautiful theory was killed by an ugly fact. Personally, I think there are no ugly facts. There are just facts. And beautiful theories are those that are both grand enough to teach us something fundamental about the very structure of the cosmos and also make detailed and accurate predictions. As we move forward, please keep both of those ideas in mind. It's truly splendid to aspire to know, as Einstein so poetically stated it, God's thoughts. In the lectures that follow, we will explore both the two proto-unified theories that we have, as well as other things that we know that are not yet well covered by either theory. We'll also learn about ideas that scientists are exploring that might further unify our understanding of the universe, and hopefully clarify those mysteries for which we don't yet have an understanding. We'll even cover some of the experimental techniques employed by the scientific community, as it's only through careful comparison of data and theory that we will finally know that we got it right.